general of dynamics was dictated by the value. And since then, there is a lot of work about oh, in fact, there is a lot of work about it, but I used to show some of them. For example, random scenarios associated to the Fq linear microscope, which are irreducible divisors of T to the n-1. And there are a lot of other work. Okay. And but the new study is the term, and from this term, we decide the graph of the quadratic coefficient. Why over the integral characteristic? Because in all characteristics, the shape is very close. Here, cycle are 3, and 3 completely different in the other side. And this 3 is not met. It is very difficult to understand what happens in all characteristics. Then we decide to do that. We need some notation. We denote Tn, the oriented type of length n. Tau 1 will be the graph of 2 points, one here to the other. And tau I is a tree obtained the tree we are two vertices adapted to this point. For example, here we have tau 1. Of these last points, we have 2 points to get tau 2. At each of one of these points, we have 2 points to get tau 3, and we get tau 4. And finally, Tn comma tau I. It is the graph obtained in Tn, and each point of the cycle we attach a tree isomorphic to tau I. And we denote like this the region union to graph, and like this the region union of several graphs between them. Well, for now, Q will be an even from power. The trace function will be denoted by here from F2 to F2. And the second result is the classification of the function graph of quadratic. We know that if b equal to 1 for this trace 0, then the graph is isomorphic to x squared in space to b in x. And if b is different from 1 and the trace is equal to 1, the graph is like that. Where this alpha there can be any element satisfying this condition. The new result is if the trace of AC is 0, then in fact this quadratic polynomial, of the graph of this quadratic polynomial, is the graph of the square matrix, and the graph of the square matrix is well known. Now, if the trace of AC is not zero, it is one, then we have in fact that the graph of F is homomorphic to the graph if x squared is alpha, where alpha is a normal element. A normal element is just an element of F to the n. And in here, then alpha is a normal element of Fq over Fq. In general, a normal element of F to the n over Fq is an element such that alpha and it conjugate form a basis of F to the n over Fq. Using this change of variable, we get we define a new function from F2 to the n when where we use that do a shift of one place and the last element becomes the first. We add one to this element and we get that the graph of F is a graph of G. If we iterate the n times, for example, we get that we have one at each coordinate. So the image can be equal to the beginning element. This means that if we have a cycle, this cycle can have a length divisor of n. But if we do this 2n times, we get the initial point. This means that in fact, if we get a cycle of length d, d must be a divisor of n, but not a divisor of n. With this, we get uh, we get this result. In fact, L times 2 power n plus 1 root 2 over all divisors of 2n, but there are no divisors of n. You take R divided by K without this cycle, and you can plot with this map G. So, for we can call the number of cycles here in the graph of A, and then we get this notation for the graph, where this number is like that with this module transformation. For example, we want to know what is the graph of x over Fq9. We use the formula before we get the number of cycles of this length. Well, the next case is when d is equal to 1. If d is equal to 1, I wanted to show the slide where we did the classification with this idea. But in fact, in this case, when d is equal to 1, the graph of f is homomorphic to the graph of x squared plus x. And x squared plus x is the linearized polynomial of x minus 1. And then this becomes a good case of a work of relative finite. Then we use the of relative finite for the particular case where even though polynomial is x minus 1, then we get the function of f. Okay, we have here it will be then it connect each connected component will be of this behavior. A cycle and this and length attached to this vertical. And this number is just the order here, the order of x minus 1, the modulo h. And for example, we get here an example of x equal to 1. We have this function graph. The interesting is that all the trees are all isomorphic with the that is good. And after that, we need to we have the next case, the last case, when b is different from 0, different from 1. What happens? In fact, we don't have yet our tools for type. We don't know what is the highest behavior of type, but we have the behavior of the tree. To do this, we need different tools. In fact, we have a sequence of endpoints here, such that each point of the cycle each point of the sequence is a solution of this equation. We get in the 0, we get B1, B2, etc. And in the last point of the sequence, we get irreducible polynomial over Q. If this happens, then we get another set of n points containing the previous n point, such that they are the solution to the same equation of the same kind of equation, but over the Fq square over a degree to space. And this one, this polynomial, would be irreducible over F. And with this, we can determine the behavior of the tree. In fact, it becomes, it depends of the element B. It must be a Bn element over Q. And we solve this equation to take B1, B2. As we get an irreducible polynomial over F to the n. Then, when Q is written like that, because Q must be an extension of F to the n to have this functional graph over Fq, and we write the power of 2 as a product of a power of 2 and number n, which is an odd number. And in this case, we get that all the components connected components are of this behavior. P is has a profundity times S, and we don't know how the shape of the. For example, if we get B in square root of E via the generator of E4, the graph will be like that, a circle, and each point we have this an arrow. Why? Because x squared E will be is irreducible. And then if we get here, for example, 4 or 12, they are odd number. Then the profundity of the field is doubled. Another example, if we get, for example, B, the root of this equation, it is here, we can solve 3 times the equation. If the square will be B, with B1, with B2, and with B2 no. And we get a profundity of 3, and then get a power which is 2 times 5 times some odd number, the profundity is double. I didn't do an example where the profundity is 4 because I can see a lot of that. Well, and the remaining challenge is to know the cycle of the functional graph for any value of B.
Are there any questions or comments for Victor? If not, let's thank him again.
Gracias, Vista. Okay.
So our next speaker is Cícero Carvalho from Universidade Federal de Uberlândia, and he's going to present his work on the second lowest Henry rates of certain particles.
Okay, thank you, Juliani. So I'd like to start by thanking very much the steering committee of the FQ meetings for agreeing that Fq16 could take place in a galaxy far, far away. And I also thank the organizing committee for agreeing that I could talk in this meeting. So my talk will be about the second lowest hammer rates of certain codes, and there's a joint work with Anupur Pataya from India. So I'll start just by establishing notation. Okay. Well, by this time you already know what FQ is. So let me just say that the code of length C is of length M is an FQ subspace of FQ to the M, and the vectors of C are called code words. Given in double alpha, we know that the weight of alpha is just the number of non-zero entries. The minimum distance of the code is just the minimum of the weight of non-zero codes. So in this talk, we work with the so-called evaluation codes. I'll talk a little bit about them. Evaluation codes, we start with a set of points in the affine space of dimension m points in this case, and you note by this I sub x the vanishing ideal of x, which is just the ideal formed by all polynomials in this polynomial ring, which are 0 in every point of x. And then we have this evaluation map from this quotient to Fq to the m. So we take a classical polynomial, evaluate the representative in the points. Of course, this is well defined, evaluating every point. This is clearly an FQ linear transformation, and moreover, it's an isomorphism. So the number of points of x, which is m, is equal to the dimension of this quotient, seen as an FQ vector space. Okay? And to produce the code, we just take L, an FQ subspace of this quotient, and then the image of this L using phi is a subspace of FQ to the M, so it's a code. It's called the evaluation code associated to X and L. Okay? And these codes may be studied using tools from Gröner basis theory, which was introduced by Bruno Buchberger in his PhD thesis in 1965. Okay, so I'll talk a little bit about this theory. So I'll denote by M the set of monomials in a polynomial ring with coefficients in a field K. We endow this set with the so-called monomial order. This is just a total order in the set, such that the 1 is the least monomial. And if you have an inequality, multiply both sides of the inequality by the same monomial. The second inequality still holds. Now, a polynomial, non-zero polynomial is just a finite sum of monomials, possibly multiplied by some coefficients. So there must be one of these monomials which is the greatest monomial, and it's called the leading monomial of the polynomial. Okay? So now let's take I an ideal in the polynomial ring. We say that finite subset is a Gröner basis for the ideal if the leading monomial of any non-zero polynomial in I is a multiple of the leading monomial of one of these sets. Okay? And one can prove that such a set is a basis for the ideal in the usual sense of set of generators. Okay? In Buchberger, he provided an algorithm that starting with a set of generators for the ideal, enlarges the set, adding other elements of the same ideal, so that the resulting set is a Gröner basis for the ideal. A very important concept in this theory is the so-called footprint, which is the set of monomials which do not appear as the leading monomial of any polynomial in the ideal. Okay? Buchberger proved that the classes of these monomials form a basis for this quotient, seen as a K vector space. In particular, in the set of the previous slide, we know that this is an isomorphism. So we know that the cardinality of the x, which is m, is the dimension of this quotient. So is the number of monomials in the footprint. Something that I will use many times in this talk. Okay? So one may show that a finite subset of I is a grammar basis for I if and only if the footprint is the set of monomials which are not multiples of the leading monomials of any of these guys. So this result may be used to see, in a way, the footprint of the ideal. We do that by associating to any tuple like this with integral or negative entries, a monomial like this, and then we plot the points. Okay, for example, if I have just two variables, so to this point I associate this monomial. So now we plot the points corresponding to the leading monomials of a grammar basis, and then we plot the multiples of these leading monomials. The points which are not plotted are the footprint because of this result. So for example, assume that we have the leading monomials of a grammar basis for a certain ideal are these three monomials. So we plot here the point 50, which corresponds to this monomial, and then all the points in this region correspond to monomials which are multiples of this monomial simply because the first entry here is greater than 5. Then we plot the point 04, which corresponds to this monomial, and then all the points in this region correspond to monomials which are multiples of this one. We plot the third monomial. All the points in this region correspond to monomials which are multiples of this. So the points that are left form the footprint of the ideal. So maybe that's where the name footprint comes from. For each ideal, we have a different picture. So in this talk, we will work with the following setup. So evaluation codes. So now I describe the X. The X that I'll take in this talk is Fq star to the n. So this subset of the affine space. So we have Q minus 1 to the n points. Okay, this is the length of the code. Then one may prove that these polynomials generate the vanishing ideal of X, and also they form a grammar basis for this ideal with respect to any monomial order in M. Okay? Okay, so now let D be an integer. To produce the code, I take D, an integer greater or equal than 1. Then I take L of D, the subspace of this quotient, generated by the set of classes of monomials of degree D, but the exponents here are either 0 or 1. So no, so these are just product of distinct D variables. Okay? So this L of D will be the Fq subspace generated by the classes of such monomials. Then we take the image of this subspace. Then we get what in this talk will be called the torus. The range of interest is D greater than 1, less or equal than n, because we have n variables. And since we know grammar basis, so this grammar basis, for example, if we have only two variables, the grammar basis will be squared. If we have n variables, it's like a hypercube. So we know the footprint. These are the monomials which are not multiples of the D monomials there. Monomials like this, where the exponents vary in this range. Okay. Okay, so we know the footprint. So now, given an element of L of t, which is a class of monomial, we write the leading monomial of f like this: monomial of degree d, where the exponents are either 0 or 1, and okay, we want to estimate the weight of this code. Okay, so by definition, the weight of the code is the length of the code word minus the cardinality of this variety. This variety is just the number of points of x, which are 0 of x. So this is the weight. I told you before that the cardinality of x is exactly the cardinality of this footprint. And one can also prove that the cardinality of this variety is the cardinality of the footprint of this ideal, I sub x plus the ideal generated by f. And since this ideal is contained in this ideal, this footprint is contained in this footprint, so this difference is actually the cardinality of this set difference. Okay? We can also prove that the cardinality of this set difference is lower bounded by the number of monomials in the footprint of I sub x, which are multiples of the leading monomial of f. Okay? And due to the particular nature of this footprint, And the particular nature of this leading monomial, this number is exactly this, regardless of which the leading monomial of f. Okay? So, Daniel Jaramillo, Maria Vaspinto, and Rafael Villarreal, in 2021, they proved that in the case where you have 2D less or equal than n, this lower bound is attained. For example, take this polynomial, count the number of non-zeros in x, you get this number. For the case where n is less than 2D, Jaramillo and friends, they use the fact that in this case, C of D is monomially equivalent to C of n minus D. As a consequence, you have that the minimum distance of C of D is equal to the minimum distance of C n minus D. But now from this condition, you get that 2n minus D is less than n. So this n minus D satisfies this condition here. So we know that the minimum distance is the same. We can apply this formula with n minus D here. We get the minimum distance of C. Okay? Okay, now footprints may also be used to determine the second lowest heavy weight of a code, also known as next minimum weight. So this is a technique that, as far as I know, was first introduced by Robert Roland in 2010. So you take a class of a polynomial here in our subspace L of T. We just saw that the weight of the code word is lower bounded by this number. Okay? So you count the points here, you get a lower bound for the weight of that code. Now, when they show that equality holds here, you have equality if and only if, whenever you have a greater basis for I sub x, you have f, you have a greater basis for I sub x plus this. Okay? And if this is not a greater basis, so that's the case where you have equality. But if it's not a greater basis, then you don't have equality. Then you have that this footprint is properly contained in this set, the set of monomials which are not leading monomials, which are not multiple of the leading monomial of f. So the footprint of this ideal is properly contained in this region. And then you can apply Buchberger's algorithm to get another polynomial in this ideal, such that the leading monomial is in the footprint, but is not a multiple of the leading monomial of f. Then no monomial of this footprint is a multiple of the leading monomial of f or the leading monomial of h, and you get a new lower bound for the weight of this code word. Monomials which are not multiple of the leading monomial of f or not multiple of the leading monomial or a of h. So the number of these points here, they establish a new lower bound for the weight of this code word, which is of course greater than that lower bound. So it's a lower bound that can be used to determine the second lowest heavy weight. So for toric codes, we recall that if you have an element of D, you have this lower bound for the code word. Okay. After relating the variables, we may assume just for simplicity that the leading monomial is x1 to xt. Okay? Then assume that 2D is less or equal than D. We know that Jaramillo and friends proved that if you take this polynomial, you get a lower bound. And together with Patante, we prove the following. You take f to be a monomially square free. Monomially square free simply means that all the monomials are of this type that we are working. And the homogeneous polynomial of degree D, such that the leading monomial is of this type. Assume that 2 times D is less or equal than n. Then we get that this is a minimum weight code word if and only if f is of this type. So here we have other variables, x1 to xd, that have nothing to do with x1 to xt. Okay? So in other words, under the hypothesis of this proposition, we have that this is a greater basis, so the lower bound is obtained, if and only if f is of this form described. So this is a greater basis for this ideal, if and only if f is of this form. So if you want to study the second weight, we assume that if this is not a greater basis. So then for at least one j, Buchberger's algorithm will combine a polynomial like this with f. We produce another polynomial h in this ideal, whose leading monomial is in the footprint and is not the multiple of the leading monomial of F, as I have explained before. So we did some calculations and we determined the possible leading monomials that may appear for the possible leading monomials for this H. So the first is a monomial first type is a monomial like this. Second type is a monomial like this. Here, this is actually a family of monomials because you have a description of where these variables may be, where these variables may be. Here we have u variables, v variables. U plus v must be equal to d. U may be 0, but at most d minus 2. So we have, we have another family of monomials, which is this M3. So here we also describe this, where these variables may be, where these variables may be. We also have that u plus v is equal to d minus 2. Here's the range of variation of u and v. And we also have a family of this type. Here we have a family because we have these two variables, and they be any distinct variables in this set. Okay, so now we know the possible leading monomials that may appear as leading monomial of H. So now we counted the number of multiples of these monomials which are in the footprint and are not multiples of the leading monomial of F. Okay? So we were counting the number of monomials here for each of those types. Okay? So the numbers are like this. For in the first type, we have this number. For the second type, remember that the second type had u and v, but u plus v was constant. So let's say it depends on v. We have this number of multiples for this family. For the third family, M3, we have this number of multiples also depending on v. And for the fourth type, which have that xe1, xe2, doesn't matter, the number of multiples is always like this. Okay? So now it's the time to count, to decide which of these numbers is the least one. So the sum of these two could provide a lower bound for the second Hamming weight. So we did a calculation, we found that M4 is less than all the other numbers except for M3 with v equals 0, which is the least one. So we had a very distant least number. When we saw this, we were very, very, very disappointed. Because it was terrible. Because our examples showed that actually we should have NM4. This should be the right number. So we came to a block, a researcher block. But after many weeks thinking about this problem, we finally understood what was happening. What happens is the following. When you have that the leading monomial of that H is M3 with V equals 0, what happens is that this set is not a Gregory basis for this set. So again, we can apply the Gregor's algorithm. We can find another polynomial whose leading monomial is in the footprint, is not a multiple of the leading monomial of F, is not a multiple of the leading monomial of M3 with V equals 0. And if you count, then we determine this number of points here, and we showed that if you add these two, then the number is greater than N4. So we were back to N4 finally. So, okay, so this would be indeed the lowest bound for the second weight. And when 2d plus 2 is less or equal than n, we know that the minimum distance is this. So we proved that if you take this polynomial, sorry about that, this should be x, not t. We proved that if you take this polynomial with x in the place of t, then indeed you have this second lower bound is okay. And if you have 2d minus 2 is greater than n, then using the same isomorphism that Daniel Havaminian and friends used, we have that the second lower bound is also the same. You just change d by for n minus d. Okay, so here we are missing some values of d. So depending on the parity of n, we miss one or two values of d. Later we determined one of these values. But the calculations were so hard that we decided not to upload even to archive. We said, no, it's okay, let's forget about this. If somebody do this, they can have it. So, it's because our proof is ridiculous. It's just a bunch of calculations. So I said to her, no, let's publish like this. And then finally, it was accepted like this. So it's good. It will be in Journal of Audio in these applications. Okay? Okay, so this was what I wanted to say. So I thank you very much.
Are there any questions or comments?
No, no. This is kind of a very simple question, but you have done everything for torquing, but do you have a, so your polynomials are just like multiples of variables in the beginning?
Yeah, the monomers.
Do you have another family that could be that simple, maybe?
Yeah, we
maybe
were thinking
like
about, because in their Arabic paper, they study this type of thing, and they also study what they call square-free polynomials, something like that, where they work with polynomials like this, but where you can mix monomials of degree up to d. So this is also a subspace, and you can think about that too. So, but as we were starting this project, we thought about maybe we do something similar to what Sakshi did. Are you going to present your thesis? Yeah. So you see that she had a very good idea together with Sudhir. They characterized some polynomials which we had done this characterization of polynomials that attain the minimum distance, and then you can count words. So we had already done some characterization of that polynomials which attain the minimum distance. That first result I presented. Then we characterized the polynomials which attain the second lower bound. So we decided to count this word, and this is ended up being another paper, which is just accepting designs. And so now maybe we go back to this. It's a good idea.
Any other questions?
Okay.
Thank you very much for the very nice talk. It's a silly question, but you mentioned that the definition of Turing code is something more complicated.
Yeah.
Turing varieties or
Actually, what you do, you start with a certain set of points in integral coefficients. Then you take the whole of in a fine space, you take the whole of generated by these points, and then you take the monomials associated to the points in the whole, in the convex whole. So here, the idea is that if you start with just the usual case, 1, 0, 0, 0, 1, when you take the convex whole, you don't get any other point with the integral coefficients, so you get just so this is the other, and from this you may go to Turing varieties.
so the geometry of the points per se doesn't really factor in.
Maybe there's one paper using this, but I can look it up for you. But usually it's not usual. It has a relation, but I think it was Hansen, J.P. Hansen, which just this. But then sort of deviated from the original definition. His definition was also, I think, there was some limitation. But now it's more generalized, but it went to the other side, only working with monomials. I think maybe he originally he computed some things related to Turing varieties.
Okay, we don't have time for more questions, so we'll listen to everything. From the Indian Institute of Technology, Mumbai, and she's going to present her work on enumeration of minimal weight cohorts of affine Cartesian codes.
First of all, I would like to use this stage to thank the organizers to provide me this opportunity to present my work here. This is a joint work with my PhD supervisor, Professor Sudeep Gurpure at IIT Bombay. We'll start with some basic definitions of codes. So we denote with by Fq the finite field. A linear code of length n is a subspace of n-dimensional vector space over Fq, and if it has dimension k, we denote it by nk code, where the support, and for the vector x, the support is the set of indices where it has non-zero entries, and the Hamming weight of the vector is the size of the support set. The minimum distance of the code is the minimum possible Hamming weight of non-zero code words. There's a nice relation between the this minimum distance and the dimension given by the singleton bound, which says that the minimum distance can be at most n minus k plus 1, and when this equality is achieved, we call such a code to be maximum distance separable, MDS. Coming on to the definition of dual, so dual of a code is all the vectors x which are orthogonal to every code word in C. But this is about basics. The main object of our interest is affine Cartesian codes. These are evaluation codes that has already been defined by Professor Carvalho, but the definition here goes like this, that we choose m subsets of the finite field Fq of size di, and we arrange them in the increasing order of their sizes and take the Cartesian product denoted by script A. And we list the points of that Cartesian product by P1 to Pn, where n is the size of the Cartesian product set, and this is nothing but the product of the cardinalities of the sets di. And then we consider the evaluation map, where we consider polynomials in m variables of degree at most u, and send that polynomial to its image to be a vector of length n, where it is evaluated at every point of the Cartesian product. This evaluation map is a linear map, and therefore its image is a subspace of Fq to the n. That is what we call the affine Cartesian code of order u and length n. Where by convention we take u, for u is equal to -1, it is the zero subspace that is defined by convention. These codes were first discussed by Geil and Thompson. These codes were first discussed by Geil and Thompson in 2013, whereas the term affine Cartesian codes were introduced by Lopez, Renteria Marquez, and Villarreal. And these codes are vast generalizations of very widely studied codes, namely Reed-Solomon codes and Reed-Muller codes, which many of you are familiar with. And when we take the integer k to the summation I from 1 to m di minus 1, that is the maximum possible dimension this code can have, we see that we attain the full space, and therefore the only cases of interest are for values u in between 1 to k. And Reed-Solomon code is a special case when we are dealing with affine Cartesian codes in one variable, and Reed-Muller codes are obtained when we take each of the subset a1 to am to be the full space Fq. For an example, if we consider here, we are in the case of two variables over f of the field f7. We take two sets a1 and a2. A1 has size 4, A2 has size 5, and then we take the Cartesian product, which is represented by green dots. In this, these are the evaluation points. Then we consider monomials of degree at most 5, such that the degree in the first variable is at most 3, and the degree in the second variable is at most 4, which is 4, di minus 1, and it represents a monomial basis represented by the blue dots, which is this trapezium. Whereas if we this triangle corresponds to the Reed-Muller code when we evaluated all the points of this space. So this becomes a code of length 20, where 20 is the number of green dots, the dimension 17 corresponding to the blue dots, and the minimum distance is 2, which is not actually represented here in the graph but can be understood from the graph itself. So our object of interest is minimum weight code. So these are the basic parameters of affine Cartesian codes, which are determined by Lopez, Renteria, Marquez, and Villarreal in the paper where they defined a affine Cartesian code. So we have a nice combinatorial formula for the dimension and also for the minimum distance. The duals and generalized Hamming weights of affine Cartesian codes are also determined by Whelan and Datta. And it's interesting to note that the dual of affine Cartesian code is a generalized affine Cartesian code where there are certain weights attached to each of the coordinate w1 to wn, which are dependent on the polynomial gi's, which are based on the choice of the sets that we take. So our object of interest is minimum weight code words. As we have seen that these are generalizations of Reed-Solomon and Reed-Muller code. So we start with what do the minimum weight code words of Reed-Solomon code look like. So Reed-Solomon code has minimum weight code words given by evaluations of the polynomial f of the form gamma times h of ax plus b, where h is a product of linear factors of this form, and it was given by Tolleson in 1994 that the complete weight enumerator. And from there we have this result that the number of minimum weight code words for the Reed-Solomon code is q minus 1 times binomial n choose k minus 1, where this is the formula. Coming on to Reed-Muller codes, we define certain notation. So this m choose LQ denotes the Gaussian binomial coefficient corresponding to the number of L-dimensional subspaces of the m-dimensional vector space over FQ, and we denote by GLMFQ the group of m cross m non-singular matrices. Then we define the affine general linear group, which is basically mappings from the space FQM to FQM given by that the vector x goes to AX plus B, which can also be represented in the matrix form, and it is shown that the composition of the maps is same as the matrix multiplication. So these are two definitions of the affine general linear group, and these are equivalent. Coming on to Reed-Muller codes. So Delsarte, Goethel, and McWilliams in 1970 gave a very nice characterization of minimum weight code words of Reed-Muller code, which says that every Reed-Muller code is given by evaluation of the polynomial f, where f is equal to gamma times h composed with sigma, where sigma is an element of the affine general linear group, and h has this nice form where I goes from 1 to t, 1 minus xi to the q minus 1, and this is basically a product of linear factors again, and moreover they also give this formula for the number of minimum weight code words, which is purely combinatorial. So this motivated us to think about what do the minimum weight code words of affine Cartesian codes look like and how many are there. For that, we know that there is no characterization known for arbitrary choice of the Cartesian product A, whereas Guile showed that there exist cases where it is not given by a product of linear factors. And then Carvalho and Neumann in 2020 considered a special case, both of them are present here, and they consider the special case where they consider the sets in the Cartesian product to be subfields, and moreover they assume that these are nested subfields. That this first set A1 is contained in A2 and these are all subfields. So we count the number of minimum weight code words in this case. So we fix certain notations. We take the Cartesian product to be this product of F1 till F lambda, where F1 to F lambda are distinct subfields, and these are repeated mu I times in the Cartesian product. F1 is repeated mu1 times and so on. Then we define the partial sum St, that is mu1 plus up till mu t, and then it is easy to see that when we compare the two definitions, the Cartesian product from A1 to An and this Cartesian product from F1 to F lambda, it is easy to see that whenever I lies in between the St minus 1 to St, basically the Th block that we call it, then all the AIs are equal to the Th subfield, Ft. And therefore all the DIs are also equal to P to the RT in this case. The, then they define the affine group. We have already seen that the affine general linear group has a nice structure in terms of matrices. But when we consider the Cartesian product, we have this definition that the affine group associated to the Cartesian product are basically restrictions of the elements of the affine general linear group such that they are bijective on the Cartesian product A. And this is a characterization given by Carvalho and Neumann that every minimum weight codeword in this case of nested subfields is given by evaluations of the polynomial f, where f is equal to hk omega times composed with phi, where phi is an element of the affine group, and hk omega is again a nice polynomial which is a product of linear factors again. So the crucial parameters here are k and omega, where k is such that this dk is greater than equal to dj plus 1 minus l, and omega is a subset of size dk minus dj plus 1 minus l, where j and l are uniquely determined depending on u that we start with. So, since the definition of the affine group associated to A was a bit abstract, so in the case of nested subfields, we tried to characterize it in terms of matrices, and we see that the affine group associated to the Cartesian product A is nothing but those elements of the affine general linear group, where A has this block-layer triangular form, matrices of this form where A11 has entries from the field F1, A21 and A22, the second block, has entries from the field F2 and so on, and the translation vector B is nothing but a vector from the Cartesian product A itself. Then we come on to the enumeration, and then using this characterization in terms of matrices and the characterization of minimum weight codewords given by Carvalho and Neumann, we say that every minimum weight codeword is given by evaluation of the polynomial f of this form, where we have replaced xi with li minus mu i's, where L1 to Lj plus 1 are linear independent, linear homogeneous polynomials, where whenever I lies in the Th block, this polynomial Li has entries from the field Ft, and it is only in the variables x1 to xst using the block-level triangular structure of the affine group. And if we denote by NQUA, then set of minimum weight codewords of affine Cartesian code of order U, then it is easy to see that when we have U is equal to -1, that's just the zero space, and there is no minimum weight codeword. And when we have U is equal to 0, it's the repetition code, and therefore the number of minimum weight codewords is Q minus 1. So now we consider the case when U is in between 1 to K. We write U of this form, where J and L are uniquely determined, and this is the generalized obtained using generalized division algorithm. As we've already seen that this minimum weight codeword is is obtained using transformation of the polynomial hk omega. So the crucial parameters here are k and omega. So we write n as a union of some sets nk's, and each nk is now a union of some sets of the form nk omega, where nk omega has this nice form for a fixed k and omega. It is evaluation of the polynomial f, where f is given by gamma times hk omega of sigma x, where k and omega are fixed in this case. So we try to find, and then we see that this set nk omega is nothing but orbit of certain group action. So let's recall what the group action is. So we start with the group G and a set X. A group action is a mapping from G cross X to X which satisfies these properties. For an element x in X, the orbit is given by the all possible images of the set X under this group action, and the stabilizer is all those elements in the group G which fix this set, fix the element X. And there's this nice relation between orbit, the size of the orbit and stabilizer, which is given by this orbit stabilizer theorem. Now, in our case, we consider the group GA corresponding to the Cartesian product A to be Fq star times affine A, which is elements of the form gamma comma sigma AB, where this A is a Bloch-Level triangular matrix coming from G, B is the translation vector coming from the Cartesian product A, and gamma is an element of the is a non-zero element of the field. And then we consider the group action that the group GA acts on the set of minimum weight code words of the corresponding to this fixed k and omega, such that the polynomial code word corresponding to the polynomial f is mapped onto gamma times c of g, where the c of g polynomial is f composed with sigma a. Then it is easy to see that this set nk omega is nothing but the orbit of the polynomial corresponding to the code word hk omega under the action of this group. So using the orbit stabilizer theorem, it suffices to determine the cardinality of the stabilizer. So the stabilizer for this particular element will consist of elements gamma comma sigma AB in GA, which satisfies this equality gamma times hk omega of sigma AB is equal to hk omega, where this is a polynomial equality. And so we consider different possible choices of k and omega and try to consider separate cases accordingly. So now we were supposed to find the stabilizer. So if we start with an element of the stabilizer, there are three variables involved, gamma, A and B. So we see that the kth column in the matrix A has all these entries 0 from 1 to j plus 1 except the kth entry. The vector B also has all the values 0 from 1 to j plus 1 except kth entry. The entry AKK is non-zero and gamma is exactly equal to this. So there's a unique choice for the gamma. And considering we try to, then we see that now for the choice of the set omega, if we call S to be this dk minus dj plus 1 minus L, we consider another group action we consider another group action for one variable where the set omega is being mapped onto akk omega plus bk, which is nothing but multiplying each element with this. And using this group action, we see that there is a nice relation between the stabilizer for each of these omegas, which is independent of the choice of the representatives and given completely by this combinatorial formula. Since we have already seen u is, and also in the in the matrix A, the Rth diagonal block also has this nice structure where R corresponds to the block which J plus 1 belongs to. So this also has this Bloch-Level triangular structure again. It's one of the block of the complete matrix A. We have seen U is equal to dj plus 1 minus L, but in the case when L is equal to dj plus 1 minus L, the polynomial hk omega converts to hj plus 1, which is now independent of the choice k and omega as well. And in this case, we have the nice formula here, where this product I from 1 to j plus 1 di corresponds to the number of choices that we have for the translation vector b, and this Gaussian coefficient corresponds to the number of choices that we can have for the matrix A, and this q minus 1 is not considered U for the orbits. In the case when L is strictly less than dj plus 1, we have this n as a union of n k's, but we see that whenever we take two integers k1 and k2 in between 1 to j plus 1, whenever they belong to the same block, these sets are identical, and whenever they belong to the different blocks, the sets are disjoint. So this union basically turns to be an equality, and therefore the total number of minimum weight code words is nothing but summation of n j plus 1 plus counting once for each of the block from first to r minus 1th block. And now we try to find this value for each of the blocks, which is And in this case, we have found this value. So when we have this nqj plus 1, we see here that this is completely independent of the variable k here. And for the omega, we have these many choices. Whereas when both k and omega are involved, we have this formula where we count it once for each block. So this is the final formula that we have. And for an example, if you can, and as a corollary, we deduce the results for the Reed-Solomon code from our result just by substituting the values. Similarly, for Reed-Muller codes, we have this. We substitute the values in our formulas and we obtain the result. Yeah, there's an example here. So if we consider the Cartesian product F2 cross F4, so it's a case of three variables where the first two sets are identical. The interesting case here is the case when u is equal to 4. In this case, the set of minimum weight code words n should be n1 union n2 union n3. Whereas since the first two are identical, F2 plus F2, so n1 is equal to n2 and it's considered just once. So the number of minimum weight code words is given to be the size of the set n1 plus n3, where for n1 we have 288 code words and 72, which gives us the total 360 code words. If you're more interested, this work is available on archive.
Are there any questions or comments in this section? No. Okay, so let's enter. So the last speaker of this morning's session is Sajad Salam from Universidade Estadual de Rio de Janeiro, and he's going to speak on FQ matching points of zeta functions over n, the loci of genus 2 curves with n-ends with Jacobians.
Thank you for the presentation. Thank you for present my talk. So this is based on a joint work with the Elira Shaskar, George Melo, and Tony Shaskar. This is available on the archive. So the main focus of this paper is divided into two parts. The first part is to computation, mathematical computation on the certain hypersurfaces, and especially for the certain finite fields that is listed here. And then approximate the zeta functions for this hypersurface. The second part is try to use this the points of this hypersurface to create Fq system, isogenic based Fq system using the Jacobians only. So for today, I only will talk about the first part. Okay. This is the outline of my talk. So first, let me define what is the genus 2 curve. Actually, it is a hyperelliptic curve that is covered by a map. I mean, there is a covering map from C to P1, the projected line of the P2, and one can get some sort of equation for that curve. So the importance of the genus 2 curve and their Jacobians in the algebraic geometry and cryptography is well known. So by the Jacobian, we mean the smallest abelian variety that you can embed your curve inside it. So this is the two-dimensional abelian variety. And we say that the curve has n split Jacobian if there is an isogeny on the Jacobian through the product of two elliptic curves, the kernel Z over Lz of 2, and here we have two elliptic curves. So these conditions, existence of isogeny of the N, lead to certain polynomials. I mean, you can describe that condition where with a certain polynomial using the Lusa invariants associated to the curve. So this polynomial defines a certain subset of the moduli space of the genus 2 curves. So here are the list of the Lusa invariants associated to one curve here by that polynomial of 86. So the last one is important because it is the discriminant of the polynomial. So to have a smooth curve C, this must be non-zero. Okay, what is the moduli space? Actually, this is the isomorphic class of equivalent classes of smooth, irreducible, and projected curves over K. K can be any field of characteristic, any characteristic. So if you consider this map, the image inverse of any integer here defined a moduli space of genus G over K. It is well known that this is a variety, algebraic variety of dimension 3 is 3 times to minus 3 times genus minus 3 for any giant genus. So for any genus larger than 2, a moduli space is a singular algebraic variety. So a class or a point in this moduli space is singular can now give the automorphism group of the algebraic group C is non-trivial. So we are interested on this subset Ln, actually Ln, this is Ln, where we have the curve with Ln splits, and also M2, the genus 2 moduli spaces.
And we related this to this weighted projective spaces. Okay. So let's see. Another importance that we choose these hypersurfaces is because those are related to the Hubbard surfaces, which are certainly defined here. So if you get the A to be the moduli space of principally polarized abelian surfaces, so it is known that you can see it as a quotient space of the action of this group, this symplectic group of Z, or the Siegel upper half space of degree 2. See the Siegel upper half spaces. So the action can be seen for any plot matrix in this group, and any matrix in the Siegel upper half space, you can define the action in this way. So for any capital data and integer, you can define as the set of all matrices in the Siegel surfaces, upper half space, that satisfied in these equations for some integers. So then we can define the Humbert surface H delta of discriminant D delta is the image of N of delta under the canonical map from the Ziegler upper space to the action to the A2 module of the embedded. So it is well known that this is non-infinity, and it can only have delta be a positive integer, and delta is equal 1 or 0 on 4. So Humbert surfaces represent the abelian surfaces with additional isomorphism structure, real multiplication, or those which are isogeneous to the product of the curves. So we choose this hypersurface, the look here of LN, because actually this is a Humbert surface with, which contains those curves that are split Jacobians. So the Ln is exactly this Humbert surface. So in this view, the geometric view to these hypersurfaces is because of the study of the sort of surfaces inside the multiple series of surface. Okay. So let's see what is the weighted projective spaces. We can consider an K-bar, the algebraic closure of K, and consider the non-zero elements that acts on these Finite spaces by this way. So where we have the weights, the weight vectors given by the positive integers. So the weight projective space can be seen as quotient space of this action, and the usual projective space is nothing but those weighted projective spaces that have the weights 1, 1, 1. Okay. So the weighted projective space is called reduced if the GCD of the weights is equal 1, and it's well formed or normalized if that satisfies these conditions. Okay. It can be shown that any weighted projective space is going to the reduce and well formed 1. And for any given weighted projective space, we use this notation to show the set of the k-rational points. I mean those points that have a representative with all components in the base root. Given any weight and any point on the weighted projective space, we define this set. Those indices that the point has non-zero component. Then the locus, the singular locus of the projective spaces is given by this set. So only when we have the weight usual projective spaces, this set will be empty. But for other cases, we have a closed subset of the projective space. So in the line schemes, you can see that any weighted projective space is the approach of this set of homogeneous polynomials in x0 xn, where we have the weights for each algebras. Especially for any monomial in this form, we can define the degree by this sum. And so for any element, I mean any polynomial in this ring, we say that it is weighted degree D if all of its monomials satisfy this condition. I mean, has the weighted degree D. Okay. So any weighted variety inside the weighted projective space, we mean that approach of the ring, this ring, quotiented by this ideal, where we have certain polynomials with certain degrees. So any weighted variety in the P and W can be defined this way. In special case, if you have one polynomial, basic polynomial, so this approach defines the hypersurfaces, I mean weighted hypersurface in the projective space. For example, for L2, actually this is the L2. For Ln, we have certain polynomials, the weighted polynomials. Here, the special polynomial for the case n equal to, and its degree is 13. So, the idea is in the first part of our paper is to count the FQ rational points on this. So, let me remember that for any point, the action is defined by the set. So, the idea is to use the orbits and the stabilizer method to count the FQ rational points. So, if we have a point and we define the set, those means that we have a coordinate on 0. So we define KOS, which is of those weights that WI that belong to this. Then the stabilizer is given by this low lambdas in non-zero lambdas in the base field that satisfies these equations for all our i's. So the order of this stabilizer is given by this number, GC of KOS and Q-1. So the size of the orbits is determined by this value. Then, if we consider S as a subset of these indices, we define NOS with the number of the points of this affine space minus origin that have xi different 0 for I and xi equals 0 for I outside of S. So we have the cardinality, this number will be Q minus 1 power the number of the elements in S. So the number of FQ points contributed to by these points can be calculated by this quotient, which is an integer. So summing all of the subsets and the subset of T and the indices, we can get this formula for the FQ rational points of weighted projective space dimension n. So here for special W, when we have all weights equal 1, the formula is given in the second way, this way. And if we suppose also the weights satisfy this condition, we will get the same formula for the FQ rational points. So this formula gives a number that counts the FQ rational points on the projective space. So let's go back to the hypersurface. For any hypersurface that is defined by a polynomial, we update the maybe this is any variety in degree di. So we can define this set the rational points correspond to the orbits of the actions of this non-zero element to these sets. So we have these extra conditions here. So in the same way, we can see that the number of the FQ rational point can be calculated this formula for general weights, where we have this constant is the number of the points which support S, such that we have that satisfies all of these conditions. Okay. So in the usual weighted projective spaces, there are some conjecture, but it is known that as a theorem, this Osman conjecture, and it's called by Serre and Sorens. So this gives an upper bound for the K rational Fk rational point on outer surfaces where we have the degree less than Q plus 1. This one. And for D larger than Q plus 1, this is trivial 1, which will be equal to the number of the base projected space. And also there is certain hypersurfaces that attain this bound. Here we are P n equal to the cardinality of the projected space. So there is another bond which is better than this one for the hypersurface, which is 2 by power is red. Okay. So in 2017, I will be consider the same problem for the hypersurface in the weighted projective space and state the following conjectures. If you have a weight that satisfies this condition here, the first weight is 1 and the other one is sorted. And this common multiplier of the weights divide the degree of the hypersurface, then you can get the maximum value of the FQ rational points of hypersurfaces of degree D is the minimum of these two values. And they also recently showed that the above equality holds for certain weighted homogeneous polynomials. They also prove the conjecture for assuming this case, W1 is equal to 1, and for any dimension. So there is another conjecture about the cardinality, which is generalizing the Chevry-Warren theorem for weighted hypersurfaces of the degree less than Q plus 1. In the it is a congruence relation model Q. Okay. So here is the equation that we have for L2 in terms of if you assume that the exponent are the J2, J4, J6, J10, the innocent variant, you can explain the hypersurfaces used by this polynomial. Its degree is 13. So for L3, we have a polynomial of degree 18, the repeat polynomial. For L5, we have a polynomial of 115. So that characterizes this sort of curves. So computationally, working with two polynomials is very fancy. But we did a computation for F2 and F3 in the paper. So for today, I prepared some slides in the case of F2. Here we have this formula for finding the FQ rational points. We suppose that S is a subset of these indices, 0 to 3, and this is the number of indices that have X i's beyond 0 for all I integers. So if you restrict ourselves to the characteristics 3, then we have the degeneration of the polynomial. So the polynomial model 3, we will get this shape. So we have a lot of singular points in this case. Here is the list of the numbers for powers of 3. So we have these numbers. And almost 70% of the points are singular because of this convergence. But in the characteristic 5, the polynomial will get this shape, model 5, and we get these numbers for the powers of the 5s. And you see that here the singular numbers is reduced. Because this is an irreducible polynomial in the model, in the characteristic 5. So our observation is that the cardinality of the rational points satisfies some sort of inequality. And also this is the bound which is stated by the algebraic conjecture, holds also for the L2, L3, and L5. And The zeta function, which is defined in this form for any projective varieties, in the case p equals 3, using this number, we approximate the zeta function as a fraction, rational function. So for the characteristic p, using those numbers that we calculated, we estimated this one. Okay. So here are some references, and this is the integral which proved the certain case of the conjecture. And here are two other work in the progress that we are considered. In this paper, we consider the theoretical background on computation, and in this one, I am going to study the rational points or the rational number. So the extensions of it. Okay, thank you.
Any questions or comments?
Yes, these hypersurfaces that meet the upper bound, are they reducible?
Well, for case 2, it is not reduced. It is irreducible. For 3, but in the case when we have the characteristic for 3, the L3 and L2 are reducible.
Any other questions? No, let's